Welcome back to this course on nanostructured materials, synthesis, properties, self-assembly and applications. Today we will start the first lecture of the second module, basically on the synthetic methodologies of obtaining nanostructures. In the previous two lectures, we introduced you to the basics of nanoscience and nanotechnology. What are nanomaterials, what properties they may have which are different than bulk properties, and some idea of where nanotechnology can take us, some applications. Very briefly we went through that, and we also gave you some idea about the two basic methodologies that people use. One is the top down approach and the other is the bottom up approach. So, we would be now discussing more in detail about each of these synthetic methodologies. So, in the first two lectures of module 2, that is this lecture and the next lecture, we will be studying one particular method of synthesis. Let me tell you that the low temperature methods are basically bottom up approaches. So, and another word which is used for low temperature methods is chimie douce, which in French means soft chemistry. So, the first two methods which I will discuss in this course are the sol gel, which is also can be a citrate gel method depending on if you are using citric acid as one of the polyhydroxy acids for the formation of the sol. So, sol gel is a general term for many of these processes, low temperature processes which form one of the methodologies of the bottom up approaches to obtain nanostructures. The other methodology that I will discuss after sol gel is the microemulsion method. So, we will have two lectures on the sol gel method and then we will have two lectures on the microemulsion method. So, what is this sol gel technique? So, in this sol gel technique, we have a process in which solid particles are dispersed in a liquid. So, this is called a sol, when you have very fine particles dispersed in a liquid and then they agglomerate together to form a three-dimensional network, then it is called a gel. So, in a gel you still have some liquid within it. So, from a sol, which is particles in a liquid, to a gel which is an interconnected system, three-dimensional network structure which still has some liquid, is a gel. So, this sol to gel transition involves hydrolysis and polycondensation. This is a low temperature process and many new materials are being synthesized which are called advanced materials for the new millennium by this low temperature route, which is called the sol gel route. Now, you can get from sol gel method, you can get powders which are microcrystalline or nanocrystalline. You can get amorphous powders, that means they do not have any crystallinity. So, they lack the long range order which is there in crystalline substances. You can make aerogels, that means you can have a porous network structure. If you remove from the gel the liquid without destroying the structure, you get a porous structure which is called an aerogel. You can also get a monolithic structure by the sol gel route and many compounds are made by this method. You can make coatings, you can make films. You can also make glasses and other ceramics by the sol gel method. So, this is a very popular method for making nanocrystalline materials as well as other forms of materials with either high surface area, very small particle size, and crystalline as well as glasses which are amorphous materials. These are two references. One is Sol Gel Science by Brinker and Scherer, then Introduction to Sol Gel Processing by Pierre, and you can also look at this book on sol gel materials by Wright and Sommerdick. So, these are all classic books on sol gel science and technology, which tells you how to synthesize or how to choose a starting material to make a particular sol, and then what do you do with that sol to get a gel, and how from the gel you can get an aerogel or a zero gel or coatings or films, etc. So, in a typical sol gel process, we are preparing making a sol, then reaction of the sol to get the gel, and finally we remove the solvent. Okay. So, in a sol you have a colloidal suspension of solid particles, and the dispersed phase, that is the solid phase, is small particles of the order of 1 to 1000 nanometers. When we react the sol and it forms an interconnected network structure, we get the gel, and so this reaches macroscopic dimensions and it extends throughout the solution. You can get polymeric gels by the agglomeration of polymeric particles made from subcolloidal units. So, from the sol we get, which is particles in a liquid, to a gel which is a 3-dimensional network structure. You get this sol to gel transition. Why one needs to use the sol gel method apart from the conventional method? Since you can make lot of new materials and which have lot of applications. So, you can make coatings and thin film applications. The conventional methods have limited materials they can synthesize. They cannot synthesize the porous materials and nanocrystalline materials, whereas in the sol gel method you can make nanocrystalline materials, you can make coatings, thin films, and the cost is quite low because it is a bottom up approach, it is a low temperature method, and it is not energy intensive as the conventional methods are. Okay. The sol gel method was developed in the 1960s and it has been improved over the last 50 years to apply to several new materials which are being discovered in the recent past. Now, the steps which are involved in a typical sol gel process, you have first the hydrolysis step, then you have the condensation step, and after the condensation step you have the gelation and you get the gel, and then the gel is allowed to age. That means it is kept for some time, and during aging and some solvent may go away, and after that you have to dry the gel and then densify it. Depending on your applications, you would like to densify or you may not like to densify. It depends on the kind of application that you are looking for. So, these are the main or the key steps in a typical sol gel process. So, you go from hydrolysis, condensation, gelation, aging, drying, and then you get a dense solid by densifying the dried gel. So, in a pictorial view you can look at, you have a solution and then you get a sol where you have these particles which are dispersed in this liquid, and then depending on what you want to do you can get several products. You can take this dispersed solid in a liquid which is a sol, you can spin coat or dip coat it and you get films. This is one application. You can pass it through some mold and draw fibers out of it. So, you can get fibers of oxides or metal fibers depending on what kind of particles are there. You can allow these particles to condense and form a network like this to form, which is a gel, and then that gel you can dry in different methods. If you dry it simply and allow this structure to collapse, then it will form what is called a zero gel. So, in a zero gel the structure collapses and you do not get this kind of a network structure anymore. However, there is something called supercritical drying. If you do that, you can remove the liquid in between these network structure to get this porous gel. This is called a aerogel. It is like a very porous structure where the liquid has been removed and the structure still remains. So, you can get the aerogel or the zero gel depending on how you dry the gel, and this will have a very high surface area. It will be catalytically very active. However, this will have a low surface area. Now, you can also get a monolith. So, if you take this zero gel and heat it at high temperature, that means sintering it, you will get a monolithic structure, which you can use like you want to use a ceramic or a glass monolith. They can be made like this. You can make fibers not only by drawing from the sol, you can also draw fibers by extruding from the gel. So, various end products are possible depending on the application. You have to treat the gel in appropriate manner to yield either the aerogel, the zero gel, the monolithic structure, or fibers or films. Now, in a typical sol gel processing, like to discuss what I just mentioned in little bit more detail. So, you have the sol, the particles are there in a liquid and you want to make a gel. So, you allow them to interconnect. So, when they interconnect, they form a kind of a 3D structure which still has some liquid inside, and then you can get the zero gel on normal drying, and under supercritical extraction you can take out the liquid without disturbing the 3-dimensional porous structure, and you get the aerogel. You can heat the zero gel into the dense solid, or you can make a film like from the sol. You can make a film which is called a zero gel film, and you can make a dense film after heating this. You can just get powders. If you dry the sol, you will get the powders which may be nanocrystalline. So, you get nanocrystalline powders. You can make nanocrystalline films, depends on what is your application. So, what a sol consists of a liquid with colloidal particles which are not dissolved, but do not agglomerate or sediment. So, they have particles which are not going to come down and sediment. So, that is a sol, and the agglomeration is due to van der Waals forces, and in order to counter the van der Waals forces, because you want to keep the particles separate, there must be repulsive forces, and these repulsive forces are important in a sol to keep it highly the particles to be highly separated and monodispersed. This repulsive force can be due to electrostatic repulsion, and this electrostatic repulsion is caused due to the adsorption of charged species on the surface of the particles. So, when you have charges on the surface of the particles, there will be repulsion between the particles and agglomeration will be prevented. This is very important for colloidal systems, where you have particles and these particles have a surface charge, and these surface charges prevent the particles from agglomerating and in turn keep the size of the particles small, and that is what you want when you want to synthesize nanomaterials. The other way, one method as I said is using charge, the other way is using some steric hindrance. So, you have a particle on which you can coat some organic layer. So, this organic layer and that organic layer will prevent these two particles from coming close. So, this works well when you have concentrated solution or dispersions, and this is also used for synthesizing nanomaterials. So, if you have a nanoparticle and you want to keep them separate, not coalescing with each other, then you coat each nanoparticle with some organic molecule or surfactant molecules, and then they form a shell kind of thing, and they keep these two particles apart. So, this is sterically you are keeping the particles apart. So, you can use either charge to keep particles apart, or you can use these kind of organic layers to keep the particles apart. Now, there is a concept in when you study sol gel science, there is something called point of zero charge, PZC as it is called. It is this point of zero charge when there is stabilization. Okay. You have electrostatic repulsion because you have charges, and so the particles are not agglomerating, and then you have this double layer at the particle. So, there is a charge on the surface and there is a charge in the liquid or on the other particle which keeps the particles away. Now, the charge on the surface of the particle will determine what is its surface potential, okay, and the counter ions in the solution will form the surface charges. So, for example, if you have hydroxides, the surface potential will be determined by reactions with the ions like H plus ions and OH minus ions. So, basically it will depend, if you have this particle in a solution, what is the pH of the solution. So, the surface potential will be pH dependent, because depending on your pH you will have a concentration of hydrogen ions in solution, and that concentration of hydrogen ions in solution will affect the kind of charges on the surface of this particle, and hence will affect the surface potential of this particle. So, you can have reactions like this hydroxyl ion is on the surface, and if you have these protons or hydrogen ions in a solution, that means the pH of the solution is less than 7, then you can form this kind of reactions. If your pH of the solution is more than 7, that means you have hydroxyl ions in solution, then you can generate O minus ions on the surface. So, depending on the pH, whether it is less than 7 or more than 7, you will have positive charges on the surface or negative charges on the surface. So, that is what is mentioned here. If the pH is greater than PZC, the surface is negatively charged. If the pH is less than PZC, that is the point of zero charge, the surface is positively charged. So, typical values are like, for magnesium oxide you have to have a pH of 12. Okay. So, if your pH solution, this point of zero charge for magnesium oxide is 12, right. So, if you have a pH of solution which is more than 12, okay, then only the surface will be negatively charged. So, if you have a very strongly basic solution, then only magnesium oxide surface will be negatively charged, otherwise it will be positively charged. However, if you have silica, for example, silica will be positively or negatively charged, that will depend on its PZC, which is 2.5, which is very low. So, if you have even water which has a pH of 7, right. So, it is greater than the PZC. So, even water will give rise to positive ions on the surface of silica, right, because you have the pH 7 greater than PZC, which is 2.5 for silica. However, in water, magnesium oxide whose PZC is 12 will not have positive charge on the surface, but will have negative charge on the surface. So, depending on what oxide or what surfaces you are using, what is its PZC, you have to use a pH of the solution to create the kind of charge that you need on the surface. If you want to create positive charge, you must know that the pH should be less than the PZC of the material. So, all this will control the degree of condensation, and the size of the surface potential phi naught will depend on the difference between pH and PZC, and this PZC will depend on the size of the particle and the degree of condensation. So, this is a very important property in sol gel sign to understand the nature of the charged surface on the particles and to understand the charges which will develop in a particular kind of solution whose pH can be varied. Now, after that you can have, if suppose you have a sol, you can get coagulation, that means the particles are trying to aggregate. If the surface potential is lowered, that is if you change the pH, then you can start getting agglomeration. which is like coagulation or flocculation it is called. So, you can do that by changing the surface potential, by changing the counter ions. For example, an increase in the counter ion concentration will result in a decrease in the thickness of the double layer, and you can also call this kind of coagulation of a colloid as peptization. So, this is done by removing counter ions, by washing or by adding charged ions, so that the double layer is restored. So, this kind of process is very important in industries. Most of the pharmaceutical industries, oil industries, etc., use all these techniques of coagulation and flocculation, and it is also important in our course here, where we are discussing how we want to synthesize monodispersed nanoparticles using the sol gel method, that is to control the size of the particle from the sol to the gel using various charges or pH around the ions. So, if you look at hydrolysis and condensation, the starting point for formation of a silica gel can be an alkoxide, like this is a typical silicon alkoxide. This R group, if it is methyl, then it is a methoxide, and you can have mono alkyl derivatives or mono alkoxy groups or dialkoxy groups or tetra alkoxy groups. Now, if you instead of the alkyl group here, if you have a hydrogen or a proton, then you have what are called the silanol groups. So, you can have the alkoxide groups, the silanol groups, and if two of these silanols come together, then they can condense and one water molecule will be released. So, when one water molecule is released, they form what is called the siloxane. So, these are terms which will occur very commonly in sol gel chemistry, where you are using alkoxy groups or silanol groups and siloxanes are formed. This from alkoxide you go to silanol by hydrolysis, from silanol to siloxane using condensation reactions. So, you can these are given below also. So, you have this alkoxide and you get hydrolyzed with water and you form the silanol groups. The silanol group can react with another alkoxy group to give you a siloxane group, or a silanol can react with another silanol to form a siloxane group. These are the condensation reactions, and this is a typical hydrolysis reactions. So, most of sol gel chemistry involves hydrolysis and condensation. Now, in reactions depend on whether you are doing them in acidic environment or in basic environment. So, in an acidic environment, so the oxygen atom in the silanol group or the alkoxy group, if you have a alkyl group here, is protonated in an acidic medium, and water or alcohol are known to be good leaving groups. So, the electron density is shifted from the silicon atom, and that makes the reaction easier for or the hydrolysis to be easier, and you can form this kind of group. So, this is the first step. The proton in an acidic environment reacts with this alkoxy group to form this OH plus group, and then it reacts with the another hydroxyl group to form a water molecule or an alcohol molecule, which leaves and giving you back a siloxane type moiety. So, if this is silicon, you have a silicon O siloxane moiety, or if this is a methyl group, then you will have a methyl oxysilicon moiety. So, depends on what kind of reagents they are. So, if your Y can be silicon, right, like this, so you will have silicon oxygen silicon, which is a siloxane moiety. So, the first step in an acidic environment is the protonation, and the second step is the condensation, where the water or alcoholic group will leaving you behind a chain of silicon oxygen silicon, which is the siloxane ring. So, from two independent silicon containing molecules, you get one new molecule where two silicons are bridged with an oxygen. So, this is a condensation reaction. Now, in basic environment, you will have nucleophilic attack by hydroxyl group or SiO minus, either hydroxyl group or SiO minus on the central silicon atom, and these species are found by dissociation of water or silanol groups, and these are the bimolecular type of reactions, SN2 type of reactions, where OH minus replaces OR minus. So, that is a typical hydrolysis, or it can be condensation reactions. So, if you look at this reaction, silicon OX and reacting with either OH minus or OSI minus, then this reacts at the silicon site. So, silicon here is has got 4 bonds tetrahedral, and that it forms the intermediate with these species. So, the OY attaches here, and then the OX minus will leave, leaving you behind this YOSI unit. So, this is in a basic environment. So, you can have hydrolysis followed by condensation in this manner. Ultimately, here also you get 2 silicons or 1 hydrogen and silicon bridged with an oxygen. So, this is a condensation reaction. So, condensation processes are dynamic processes and will depend on several parameters. Okay. Now, these parameters can be the type of precursor that you have chosen, the amount of water in your system and the amount of alkoxide in your system, the type of catalyst that you are using, the solvent, the temperature, the pH, which is very important, and the concentrations of the reactants. All these will affect the condensation process, and the stability and reactivity of silicon alkoxides, they are also influenced by steric factors. So, if you have a bulky ligand, it will slow down the hydrolysis. So, if you have, for example, silicon with 4 methoxy groups, which are small groups, its reaction will be much faster compared to a bulky group like isopropoxy group, and so its reaction will be much smaller. So, this is how the reactivity decreases. This will be having the highest reactivity because you have less steric hindrance, and as you increase the carbon chain length from methyl to ethyl to propyl to normal propyl to isopropyl, your reactivity is decreasing along this series. This is typical for condensation reactions, where not only all these parameters, temperature, solvent, pH, but steric factors also play a very important role. So, the other parameters like electron density on the silicon will influence the reaction rate of condensation. So, the electron density on the silicon will depend on what are the groups attached to silicon, whether you have an alkyl group, which is an electron donating group. So, you will have more electron density if it is attached to alkyl group. If you have a hydroxyl group, it has less electron donating capability than an alkyl group, and so this system will have less electron density on the silicon. So, this series, in this series, this moiety will have the highest electron density on silicon compared to this moiety, where the electron density on silicon will be very low. Now, depending on electron density, you will have ease in acid catalysis or basic catalysis. For example, acid catalysis or acid catalyzed reaction demands high electron density on the silicon, and so in this kind of situation it will prefer, or acid catalyzed reactions will be preferred. Base catalyzed reaction demands low electron density, and so that those reactions will lead to more branched networks, Acid catalyzed reactions will lead to more straight chains, whereas base catalyzed reactions will lead to more branched chains in these siloxane which form at the end. Now, the water ratio, how much alkoxide you have and how much water you have, this ratio is called RW. That also matters a lot. For example, if you have a water ratio of 2, that means you have OR to water is equal to 2, then the reaction converts everything to silica. So, you start with this tetraalkyl silane, and after hydrolysis, if you have this ratio of the silane and water, then the reaction will go to silica. Now, if you have a water ratio of 1, it leads to hydrolysis, but not to condensation. Okay. Here you see that you have a water ratio of this is 4 times, this is 4 and this is 2. So, this is twice the number of alkoxy groups are there for the number of OH groups, and hence as you see you have everything to convert to silica, which is, that means you have SiO-Si network all through the solid. But if you have only one, that means half the amount of SiOR4 compared to what you have here, then you will have hydrolysis, but you will not have condensation. So, increasing the water content will reduce condensation, okay, and reduction in the water content will increase the condensation. Now, the dependence of pH, as I said, is very important, and it is very different for acid and base catalyzed systems. So, if you look at this plot, this is kind of the rate of reaction plotted with pH. So, the hydrolysis rate is minimum around pH 7, whereas the condensation rate is minimum around at a much lower pH, say around 5.5 or something, and the rate is maximum around 8.5 or 9. Okay. So, this is for, of course, silica, and at pH this is around 4.5, which is the isoelectric point for silica. You have the minimum condensation. Minimum for hydrolysis is at 7, and minimum for condensation for silica is at pH equal to 4.5, which is the isoelectric point for silica. So, the dependence of the reaction rate with pH is very dramatic, and it depends a lot on whether it is an acid or base catalyzed system. Now, if you look at the solvent will also affect the rates of these reactions. The polarity of the solvent, the dipole moment of the solvent, which is related to the dielectric constant of the solvent. For example, water has a very high dielectric constant of 80. This solvent will be very different if you take benzene, which has a much lower dielectric constant. So, the polarity, the dipole moment, the viscosity of the solvent, and other properties which can break the hydrogen OH bond or the hydrolysis or proteolysis are important for the reactions which take part in the sol-gel process. So, polar solvents will stabilize the gel by hydrogen bonding, that is very important. So, when the gel is formed from the sol, if you have a polar solvent, because the solvent is still present in the gel, the polar solvents will stabilize the gel through hydrogen bonding, whereas non-polar solvents are better for systems which are not completely hydrolyzed. So, depending on your kind of system, the solvent has to be chosen to give you the right kind of mechanical strength for the gel. Now, during network formation, the objects will grow. So, a gel may not form, the sol particles or the aggregates of the sol particles may grow as the viscosity increases until a gel is formed. So, as you are going from a sol to gel, if you evaluate the viscosity is increasing till it forms a gel, and that is the sol gel transition. That is called the gel point. When the sol turns into the gel, that is dependent on the kind of solvent, because the viscosity is important, and the sol gel transition is reached when a continuous network is formed. So, when all the particles are interconnected to form one network structure through this hydrolysis and condensation, then that is called the gel point, and that is when the continuous network is formed. The gel time is determined as the time when you can, after forming the sol, how much time does it take before the gel is formed. Now, how do you know when the gel is formed? It is very simple. If you take a sol and you look at it till when you turn the fluid upside down and it does not flow, that is when the gel has formed. So, all the fluid is within the gel and it does not fall even when the container is turned upside down. So, that is when your gel has formed. So, this is a simple but crude method of finding the gel point. There are other methods, of course, by which you can study this sol gel transition. So, if you look at this diagram, on one axis you have the increase in acidic conditions, on another axis you have an increase in basic conditions, and what you start with is a monomer, that means one simple molecule, and then it forms a dimer. It may form a cyclic polymer, a particle, a small particle, say a 1 nanometer particle or a 2 nanometer particle. And then what happens if you have acidic conditions, and what happens when you have basic conditions. Okay. So, when you have basic conditions, you can see that this particle is growing to larger and larger size, and you can get a very large particle dispersed in the liquid. So, that is the sol. However, if you increase the acidic conditions, then you can get these interconnected particles, and which can form 3-dimensional gel networks. So, that is caused as you are increasing the acidic conditions and you are encouraging hydrolysis and condensation at the same time. So, you can have this kind of particle formation which are interconnected, or you can have growth of these particles from small size to larger size as you are increasing the basic conditions. So, the gel point is a point where a large number of sol particles and clusters still have not reacted. The aging of the gel is therefore a very important stage. So, although from sol to gel you have a transition, this is not at the gel point, which is not a thermodynamic event. Now, you have to age the gel because there are still more sol particles there and more clusters have to take part. So, the entire gel has to get connected. See, the gel point is the point where you form a single interconnect, that is all through the liquid you have one interconnect, but that does not mean that all the particles have hydrolyzed. There are still particles which need to be hydrolyzed, and so you need to do aging. And what happens in aging? You have small particles which dissolve faster than larger particles. This is also called Ostwald ripening. So, you will have small particles which are dissolving or which are joining with larger particles to grow bigger and bigger particles. So, as time proceeds, the smaller particles will disappear away and the larger particles will grow. So, the growth will stop when the difference in solubility between the largest and smallest particle is a very few parts per million. So, it is therefore possible to prepare monodisperse silica particles from a gel, because you through this process, which is a natural process which is called Ostwald ripening, and this is a thermodynamic process where if you have a statistical distribution of large particles and small particles, the small particles dissolve and add on to the large particles. So, the large particles keep growing, and this process of making silica using this Ostwald ripening process to give you monodisperse silica spheres from a gel is also called Stauber's process. Right. So, as we were discussing aging, we continue on that. As the viscosity increases rapidly, the solvent is trapped in the gel, and the structure may change with time depending on pH, the temperature and the solvent, but the gel is still alive because there is liquid inside the gel, and it will also have salt particles and agglomerates which will continue to react and condense as the gel is drying. So, originally the gel is flexible. As more and more branches will condense, the gel will become more viscous. This will squeeze out the liquid from the interior, and the flexibility of the gel will not be there anymore. So, the hydrolysis and condensation are reversible processes, and material from thermodynamically unfavorable points will dissolve and precipitate at more favorable points. So, thermodynamics will basically guide that which are unfavorable and which are favorable, and guide the particles which are favorable, and they will remain, and the unfavorable particle from the thermodynamical point of view will dissolve and disappear. Now, after aging, when you have interconnected the entire gel network, you have to remove the liquid which is still in the gel, and this requires drying. So, when the liquid is dried, the pores in the gel may be replaced by air, and some changes in the network structure may occur. So, but if you can maintain the structure, we get a gel which has got air inside, but the structure is intact like it was when the liquid was there, and this is called a aerogel because there is no liquid now, but the porous structure, network structure is there, and this is called as aerogel. However, while taking out the liquid, if the structure collapses and you do not have the network structure anymore, it is a zero gel, and it is a much more condensed form of the gel. So, normal drying of the gel leads to structural collapse and reduces the pore size. The hydroxyl groups on opposite sides may react and form new bonds by condensation. Cracking may occur when the tension in the gel is large, that it cannot shrink anymore, and gas will enter the pores with a thin film of liquid on the walls. This will evaporate, and only isolated spaces with liquid may be left. So, the drying process is very crucial whether you want an aerogel or a zero gel. So, if you want high surface area, you want porous structure, then you have to remove the liquid very carefully, and then you can get an aerogel. If you want a more condensed structure, higher density, small pore size, then normal drying or quick drying is possible, which will lead to the zero gel. So, if you see the drying process, so this is your network structure. In between the two networks there is this pore, and the capillary forces will be acting in the pores, and you will have the fluids in the pores, and they will be contracting as liquids are going. The surface forces in these pores will be active during this aging period when slowly the drying is taking place. Now, in this colloidal salt gel route, the metal salts in the solution, the pH and temperature control is very important, and the two steps which we discussed earlier, the hydrolysis and the condensation polymerization, are very important. Typically they are shown here that if you have a metal with the B number of water molecules, which may be 4, 6, with Z plus charge, when there is hydrolysis, you have one of the water molecules splits up, and you get a hydroxyl group, and one proton is liberated. Now, when you have this unit and it combines with another unit of this. So, you have condensation, and now from this you get two metal atoms with the water molecules which is one less than what it should be, and two water molecules go away to give you two hydroxyl groups and two protons. So, when you interact, when you just hydrolyze, you have this reaction, one proton is liberated. When you condense or polymerize, you will have two water molecules lost, one from there, one from here, and two protons are liberated. So, these processes are taking place all the time, and if you see this Z, the charge as a function of pH, you can see how these vary as a function of pH. Now, the sol gel method through the metal organic route, this is the colloidal route. So, the metal organic route, you have metal alkoxide in alcoholic solution and you add water. You can have the acid catalyzed hydrolysis, a little bit we discussed earlier. In the acid catalyzed hydrolysis, it is good to have a lot of electron density on the silicon. So, if you have electron density on the silicon, then this electron density can be attracted towards the electronegative oxygen ion, and you form this kind of bond, and the alcoholic group here can be a good leaving agent, giving rise to a silanol group. This is the acid hydrolysis, and in the basic hydrolysis you have this OH minus, and it takes up it binds to this silicon, and the silicon gets a negative charge, and then you lose a OR minus group and gives rise to again a silanol group. So, you have these two mechanisms for the acid catalysis and the base catalysis process. Now, you can see that the sol gel method, the gel time, how much time it takes to gel, or the hydrolysis rate, depends on pH, substitutions, the solvent and water. And here we plot this gel time with pH, and you can see that at a particular pH the gel time is very high, and then at some other pH the gel time is very low. So, the rate at which the acid catalysis takes place is a function of pH. It depends on the pH how this acid catalysis is taking place. Now, the precursors effect, as mentioned earlier, you can have steric effects, like if you have very small groups, the rate is very high. If you have very large groups like the butyl group or the hexyl groups, the rate will be very small. So, this is very large, and as you go along this, the hydrolysis rate will be lowered. Then electron density will affect what is the electron density on the silicon, and this electron density is related to the electron donating power of the alkyl groups or the alkoxy groups, and since alkyl groups have high electron density donating capacity, they will be very high, electron density will be very high here, and electron density will be very low there. So, to again kind of recapitulate that the sol gel method can be done in acidic conditions, where you are hydrolyzing alkoxy groups, and a reaction at terminal silicon is favored, whereas in basic conditions the reactions are favor branched polymer products, and the reaction rate increases as more alkoxy groups are hydrolyzed. Okay. In the acidic condition, reaction rate decreases as more alkoxy groups are hydrolyzed. So, there is a difference between the sol gel processes under acidic and basic conditions. Now, this also we discussed that the amount of water and the alkoxide group, the rates depend on the ratio of the water is to the alkoxide group, and you can see that it is some minimum at a certain concentration. So, you can have large rates of hydrolysis or slow rates of hydrolysis. At very slow, less concentration of water, you have a reasonable time, right, and very large amount of water, this is reciprocated. So, there is some optimal water is to silane concentration, where this comes to a minimum. Now, there are other effects like hydrophobic effects, which are important. So, this is a phase diagram of the silane, the alcohol and water. These are the three things which are in your system, and in some range of compositions you have the miscibility, and in some other range it is immiscible. So, normally it is the silane, as you see, is immiscible with water. Only when you add an alcohol you come to the miscibility range. So, it is important to know the concentration of your silane and water and alcohol. For a particular alcohol you will have a particular phase diagram. So, knowledge of these ternary phase diagrams is important to design a particular system for proceeding with your sol gel method. And these solvents, their polarity, their viscosity, their protic behavior, they all will be important to understand the sol gel process. So, the gel synthesis, you can see how silica can be prepared in diluted aqueous medium, forms a silica network, and the condensation depends on pH and metal salt concentration, and it forms a gel and with different morphologies. You can use metal alkoxides in water, and you have to use an alcoholic solvent to make the miscibility range. So, that will be the hydrolysis step. You can form 3D silica networks and then form the gel, and again get powder of different morphologies. So, these are various processes by which you can get the gel. So, we continue our lectures on the synthesis of nanostructured materials using sol gel methods in the next lecture. For today, this is where we end, and I would like you to go back and recapitulate on all the concepts that we have learned about sol gel synthesis. What are sols, what are gels, what is an interconnected porous structure, what is an aerogel, what is a zero gel, how to get films out of a sol gel process, and why is it called a low temperature process, why is it a chemical route, and why it is part of the bottom up approach of making nanomaterials. So, in our next lecture we will continue with the sol gel methods and then continue with other methods of synthesis of nanomaterials. Thank you very much.